Hello, crazy math nerds. It's Kitty Morgan here. I just want to talk to you about a little calculus today. Yesterday, you probably talked a little bit about the difference between the integral symbol without any numbers, which just asks you to find the antiderivative, and the integral symbol with numbers, and it means a totally different thing. It means to find the area between the function and the axis, or sometimes we call that area under the curve. So to do that yesterday, y'all did some Master Math Mentor work possibly. And like in number one, the answer to number one, of course, is 0. Why is that? Well, if you go from 4 to 4, you don't really go anywhere. So that area collected is 0. If you go from 0 to 1, because these are shapes that you know, what you want to find is this area here, the area between the function and the x-axis right there, and that's just a simple rectangle, and so you could just find the area of a rectangle because you can do that, and that's 1 times 1, 2, which is just 2. If you wanted to find the area from 1 to 3, then I would go from 1, whoopsie, oh, I'm not doing very well with that, 1, 2, 3. So that's 1, 2, 3. So I want the area from 1 to 3, and that's a triangle, so I could do 1/2 base times height, and the base is 2 and the height is 2, so 1/2 times base times height, and that is just 2, I think. 1/2, and that's 1, 2, 3. And then we talked a little bit about you can do the additive property. If you go from 0 to 1 and 1 to 3, then if you wanted to go from 0 to 3, you could add those together. So from 0 to 1 is 2, and from 1 to 3 is 2 as well, and so that would be 2 plus 2, which is 4. Or you could actually just color in the whole thing and use the area of a trapezoid, which is 1/2 times the height times the bases added together. Let's see if we get the same thing. So just being crazy here. So in this case, the height of this particular trapezoid is, let me get a different color. I'd like red, please. The height is right, those are your bases, and your height is right there. That's your height, right? And so that is 2. And your bases added together, this is one base, this is base 1, this is base 2, base 1 is a distance of 1, base 2 is 1, 2, 3, and multiply that times 1/2, and guess what we get? Oh my gosh, it's 4. So you can either do the area of the trapezoid, but because we had previous knowledge of those two areas, from 0 to 1 and then from 1 to 3, you can just simply add those together. So it did work. It's crazy, I know. And then we talked about also that, going from 3 to 6. No, that's not the one. I wanted to go from 6 to 10. Can we look at number 8 real fast? So if I want to go from 6 to 10, notice, and let me get this out of there, that bothers me. 1, 2, 3, 4, 5, 6. That's the semicircle right here. And there's your center. So your radius is 2, right? And so from 6 to 10 would be just the area of the half circle, which is 1/2 pi r squared, right? Half a circle. And so that would end up being 2 squared is 4, half of 4 is 2, 2 pi. But we also said that if your limits are backwards, so you're reading from left to right, which is normal. If they ask you to read from right to left, that's kind of like going backwards. The answer is going to be the negative of what you would get if you collected the area. So that's some of the things that you talked about yesterday, collecting area. And notice that these are all shapes that you know. You ended up with, a rectangle or a triangle or a trapezoid or a semicircle. So anytime that you're asked to do these, what we call definite integrals, you collect area. If you can collect area under things that you know, it's fine. But today's question is, what happens if we don't know exactly what it looks like? So here we go. This is Master Math Mentor, page 138. So let's take a look at that. So let's read the problem and see where we are. A car comes to a stop 5 seconds after a driver slams on the brakes. While the brakes are on, the following velocities are recorded. Estimate the total distance that the car took to stop. So this is actually this is going to be time in seconds. This is seconds. And this graph is actually the velocity. The velocity. And so what do we know about velocity or rate times time? Rate times time equals distance, right? And isn't that what they asked us for? So what we're going to do is we're going to use the area under these points, which means we're multiplying velocity times time to get the distance. So let's plot these points. At 0 seconds, he was going 88 miles an hour. That's way too fast. I know. At 1 second, he was going 60. Now, y'all, this is not to scale. Y'all do know that, right? These are scaled by 1. These are scaled by 10. But, you know, we're just doing a little sketch. At 3, he was, you know what I did? No, that's 1. That's right. At 2, he was 40. There we go. She was going 40 feet per second. At 3, he was 25. That's 20, about 5. And then at 4, he was 10. And at 5, he was 0. So it's kind of like a little curvy thing. It's not really a line because there's not a constant rate of change. That's a rate of change of 28. I can count. There you go. This is 20. See how the change in velocity is not constant? So this is not a line. It's some kind of curvy function. And I'm going to attempt to draw this, which is going to probably be real funny. It's kind of hard to draw the baby. So it looks kind of linear, but it really can't be. We know that. Oh, my goodness. This is really hard to do. Let's go back. That was terrible. I'm kind of doing okay. So it's really like it's probably some kind of parabolic or something like that, but it's just really a fat parabolic. Remember, these scales are not correct, right? So kind of know that. These are every 1, these are every 10. So. But here's what we're going to do. We need to find the area under the curve. And this is not a line, so I can't just do a triangle because it's not a straight line. So let's talk about what we can do to estimate this distance. So what I'm going to do is I'm going to draw a perpendicular line in green. Let's do that. There. And I am going to use things that I know. So I'm going to use, I don't like that that's not very straight. I'm going to cheat just a little bit and use my line feature. And I'm going to use a shape that I know and make it easy to estimate the area under the curve. I'm having a hard time with this straight line here, even though I have my straight line thing. There we go. So what I'm going to do is I'm going to do that for each one. I'm going to draw that perpendicular, that green line. And we're going to imagine that we're going to use rectangles to help us figure out what might be the area. And this is all an estimation that I'm going to be doing. And the first time I'm going to do it, I'd like to do this, and I'm going to use the left-hand height. So here are two sides of a rectangle. This is the left-hand side of this rectangle. This is left, and this is right. So I'm going to use the height of the left-hand side. Now notice when I do it for this particular function, see, and now that's the rectangle is all right there. When I do that, see how much over I am? And so this is not going to be perfect, but it's just an estimation. So what I'm going to do is I'm going to write the distance estimate. So the distance estimate is going to be about 1 times 88. 1 times 88 is that first rectangle, okay? Because that's how wide it is and that's how tall it is. If I draw the next rectangle, let's do this. Let's call this rectangle 1, 2, 3, 4, and 5. In the next rectangle, for rectangle 2, this height right here is the left-hand side. So I'm going to draw it. So I'm going to add to this distance a width of 1 and a height of 60. So 1 times 60. And then on the next one, on rectangle 3, we'll use the left-hand height, and that is 25. That's 40. I'm so sorry. Between 30 and 50 is 40. And so I have a width of 1 and a height of 40. And then on the fourth rectangle, I'm going to use the left-hand height. So I'm going to draw it as high as the left hand. and that's 25. And then I'm going to go to the left of the rectangle 5. See, I'm making a rectangle there. It would be helpful if I draw that all the way down. Rectangle 1, 2, 3, 4, and now 5. And that's a width of 1 and a height of 10. And if you add that all up together, you will get 223. So my approximation for this is 223 feet. So that's my approximate, that's what that's equal to, but my distance is approximately equal to that, right? Now notice that all of this area that we form by using the left hand, see how much overage we have, right? So I would think that this would be an overestimation. An overestimation. So what do you think would happen if we used the right hand? So what I'm going to do now is I'm going to erase all the pink, or most of the pink, and I'm going to use the right hand in a different color. So there you go. So the pink was an overestimation. And we're going to use what color should we use now? How about black? Let me find black real fast. There we go. All right, so now we're going to do, we're going to estimate the distance by now, see there's left and right. I'm now going to use the height that's on the right-hand side of each rectangle. So now I'm going to have 1 times, now the height of this is whatever that is, which is 60. Now this is the left, this is the right. I'm going to draw as high as that. So that's 1 times 40 plus the width is still 1, but now I'm going to draw from the right. So my rectangle is as high as the right-hand side is, and that is 25. And then 1 times, I'm going to go as high as the right-hand side, which is 10. And then, oh, look, that's weird, isn't it? Oh, my gosh, there's nothing there. 1 times 0. And if I add up all of those, I should have, let's see, I should have 125 and 35. I should have 135 feet. And notice that when I drew those, that there was a big gap between the rectangle and the actual function itself that's in red. See that? So this would be an underestimation of the area for this particular one. It's not always that. It just depends on what the function's doing, but for this one, it is not enough. I'm not doing enough there. There's a whole, see how all of this is not done, right? And all that's not done, and all that's not done. So this is a big underestimation. So I would say that the true distance is probably somewhere in between those two, because this was too much and this was not enough. So somewhere in between there would probably be the distance traveled, or a better estimation for the distance traveled. So when we're asked to do this, we use the left on this one. Go back and get my pink again. And so when you do that, that is called a left riemann sum. And what that means that a riemann sum is when you add up areas of rectangles, and when you use the left hand value as your height, that's called a left riemann sum. I bet you can guess what you call this one. This is called a right riemann sum, because you're asked to use rectangles to add up and estimate area, and you're asked to use the right hand value as your height. Okay, so that's end of tape 1. If you come back for the second video, we're going to talk about 2 other kinds, the midpoint and the trapezoid.